Functions aren't really a discrete math topic in their own right, but they're so generally useful that they show up in practically every branch of mathematics in one form or another. Now, we're not going to go into their analysis in any great detail here, rather just focusing on the specific properties that are going to be useful in analyzing the relationships between sets. Now, I know there's a lot going on here, but there are a few important points I want to highlight, and then we'll look at some examples. I think a lot of the terms will be clearer when you see specific examples of them. So the first thing I want to focus on is this part of the definition. A function requires three things. It requires two sets and a relationship between them. Now that first part is often kind of politely ignored in algebra classes. For example, you'll be given a formula like f of x equals the square root of x, and you'll be asked to find the domain of the function. But the question doesn't really make sense, since the domain of the function has to come first as part of the function's definition. Now, the second thing I want you to notice are these two requirements. The first one says that every element in the domain has to have a matching value in the codomain. And the second says that it can't have more than one. So together, these two tell us that every element in the domain has to be matched with one and only one value in the codomain. But notice that there's no corresponding requirement for the codomain. So each value in the codomain can be assigned to more than one domain value or even to no value at all. All right, the second paragraph here is just the definition of a bunch of terms, and that's the part that I really think is going to be clearer if we have some examples to look at. So what we have here is called an arrow diagram, and it shows a mapping between two sets. So to make this into a function, we need to be explicit about what the domain and codomain are. So let's say the diagram represents a function from the set A, B, C, D to the set P, Q, R, S. Now the first thing I want you to notice is that this does meet the two requirements for a function. Every element in the domain, all four of them, get paired with a function, a value in the codomain, and no element in the domain gets paired with more than one value. Okay, so now let's think about all of those terms back in the definition. First, the range is all of the values in the codomain that actually have a matching value in the domain. So for this function, that would be these three values. So the range would be the set P, R, and S. Now if we pick a value from that range, say S, then we would say that C is the pre-image of S, and we can write the relationship between these two as f of C equals S. That same function notation that you probably learned all the way back in your algebra classes. All right, now notice that R here has more than one value that's mapped to it, both B and D. And that's fine, right? Elements in the domain, elements in the codomain can be paired with more than one value in the domain. Now, if a value from the range is mapped to more than one value in the domain, then we refer to the set of all of those values, B and D here, as the inverse image of R. All right, and finally, one last thing, look at Q in the codomain. It doesn't have a pre-image. Right? There's no value in the domain that's matched with it, which is fine. The definition only requires that every value in the domain has to have a matching codomain value, not the other way around. So before we move on and look at some of the properties of functions, I want to look at two examples of arrow diagrams that don't represent functions. And we're going to start this off with the same domain and codomain that we used in the previous examples. Now the first diagram doesn't represent a function because it doesn't meet the second requirement. A, over here in the domain, gets mapped to two values in the codomain, which isn't allowed. Right, so that disqualifies this first example. Now in the second diagram, we've got the reverse problem. B doesn't get assigned to any value in the codomain, which also isn't allowed. Right? Now this is an issue we could fix. Right? If we further restrict the domain and define, let's use another letter here, and define G to go from A, C, D to P, Q, R, S, then we fix the problem. Right? Then it would qualify as a function. So now that we've got a clear definition of what a function is and what some of its parts are, in the next lecture we're going to look at a few more kind of little properties. We're going to talk about what it means for two functions to be equal, what it means for a function to be well defined. Then in the following lectures, we're going to talk about what it means for functions to be one-to-one and onto, which are the properties that we're really going to need to dig into methods for comparing two sets.